Okay, we're going to switch gears. We've been talking about QR decomposition, and we've talked about SVD decomposition, and now we're going to talk about a really important concept around what I've been mentioning before, which is this idea of stability of algorithms and the conditioning of algorithms. So we're going to talk about these concepts that are going to play a big role in terms of actually computing SVDs, QR decompositions. Remember, part of what we need to do is we've outlined the mathematics of what we want, and now we have to start talking about how stable or how robust or how well conditioned are the algorithms we're going to create to actually produce things like the SVD, the QR decomposition. Later, we'll talk about eigenvalue decompositions and even just solving AX equal to B. So I first want to introduce this concept of conditioning and then stability, okay? So today is going to be mostly about conditioning. And you'll see that it's a broader concept, but it plays a big role in numerical methods. So this is where we're going with this, is these two concepts are what the theme is going to be. This is the theme 4 of the class. And so these two concepts are going to be the next 3 sets of lectures. We're going to focus on these ideas. Okay. So these concepts are generic, even though we're going to contextualize them specifically in terms of thinking about AX equal to B. They really have a broader context in which you kind of frame them. So the problem I want to consider is something like this. Here's your generic problem. The generic problem is something like this. Take some input values X, map them to Y. That's it. Right? So this is a problem we solve all the time. In fact, a lot of, whether it's machine learning or statistical modeling or dynamical systems, it's often cast in this form of inputs to outputs. And F determines the kind of model I want to put in there. And a lot of stuff we're going to look at here initially is going to be, F is going to just be a matrix multiply. So AX takes you to a new vector Y. Okay? But this is a very generic formulation of essentially a mathematical problem or model that we want to consider. Okay? Is this kind of mapping. And then the question comes, what does it mean in terms of conditioning and stability for such a generic model? Okay? So more broadly, we can think about this as F is basically a map from some inputs X to Y. So this here, this X and little y, those are specific instances of data. Like I give you a vector X, it maps it to a vector Y. But this is a more broad version of this, which is I give you all these collections of X mapping to Ys. So this is like, in some sense, all of your data. And F is defined as this mapping. So this is actually the problem that we're trying to think about. And this is a specific instance because I put in a very specific set of data out of this X. In other words, the X here is contained within the X. Okay? So this is a specific data point. So it's a specific instance, but really I'm broadly living in a collection of X mapping to a collection of Y. Now, this is just so generic, right? Hopefully, everybody will understand that this kind of almost fits almost any kind of problem we might want to look at, right? In particular, linear algebra problems where you say AX equals B, but now I'm saying AX equals Y. So F is just a linear matrix multiply. And that's one way to think about, that's one of the specific problems we want to consider here. So I want to introduce 2 concepts. When we do this, there's going to be a couple of things that we have to think about. One is, how do I produce this? And typically I'm going to have an algorithm or some kind of numerical computation of taking X to Y, right? So that's what we're interested in, is actually computationally, how do we do this operation here of you take this data or sets of data in X, map it to Y. And so we're going to talk about this from 2 points of view. One point of view is the idea of conditioning, which is part of the title of this lecture and of these 3 lectures we're going to talk about, and the idea of stability. So I want to define these 2 concepts in relationship to this problem right here. Okay, so let's talk about the idea of conditioning. The conditioning idea is pretty simple, and it's basically the following. What is the behavior of this problem? Okay, from perturbations to the problem. In other words, I take this, and what happens if I perturb it? That's what I want to know. So the idea of conditioning is to start to answer the question, if this gets perturbed a little bit, my input, how does it relate to my output? If there's small changes here, right? That's what the idea of the perturbations is. Small perturbations in this X, what happens to my outcomes Y? Conditioning answers that question. What is stability? This is all about the behavior instead of this. It is the behavior of an algorithm under perturbation. Okay? So conditioning is really sort of the uber concept of saying, if I want to map this to this, and what happens if I have small perturbations here, what is the effect on Y? But then if you actually look at the analysis of different algorithms that might actually, in fact, produce the mapping, you want to understand what happens to the algorithm itself under the perturbations. So that's, in some sense, going to be talking about the stability of that algorithm. And what I've been making comments about is with Gram-Schmidt, when we did the QR, we talked about it doing it with Gram-Schmidt, modified Gram-Schmidt, and then we talked about this householder triangularization. So we talked about 3 different methods. So why would I introduce 3 different methods, right? That's one question you could ask. Why not just say, why not just one lecture on Gram-Schmidt and call it a day and let's move on, right? Why do 3 different things? The reason we do 3 different algorithms, the reason you have this development is because of things like this. If you perturb the algorithm, you ask the question, is it stable? Most algorithms, even the ones when we laid out Gram-Schmidt, are based upon iterations. Okay, so in other words, you start an algorithm and you start computing, and your previous results help you produce the next results, which help you produce the next results. So that's the idea of an iteration. And a lot of these algorithms are iterations. So what you really want is to have a stable algorithm. In other words, you don't want your algorithm, as you start doing iterations, to blow up. Okay, so stability arguments are really important when you start thinking about detailed ways to actually do computations of a problem. Okay. All right, so this is the main ideas. What we're going to spend today talking about is about conditioning. We're going to define the concept of conditioning in a more specific and rigorous way. And then from that, we'll talk about it, especially in the context of AX equal to B. And then as we go forward in these next set of lectures, we'll also start to talk about the stability of algorithms as well. Okay, so all of this is sitting under numerical analysis. One of the things that numerical analysis does is it evaluates algorithms for these two kind of concepts that are there. It's one thing to just write down something that works in theory. When you actually go compute on a computer with numerical round off in there, you want to make sure you have stability of an algorithm. Okay. So let me erase this and then we'll start getting to it. All right, so we are talking about conditioning. So let me erase the word stability for now and just focus in on conditioning. So what we're going to try to do is start thinking about this idea of conditioning. And in fact, I'm going to introduce two concepts within the structure of conditioning. Something is well-conditioned, or something could be ill-conditioned. And what is the difference? Now, the words are actually given away, right? So you want something that's well-conditioned, not ill-conditioned. Usually the word ill is never used in a good sense. Something is ill-conditioned, it's probably going to be problematic for you, okay? So let's talk about the two concepts. Well-conditioned, what it means, remember, conditioning is if I have small perturbations, what happens under small perturbations? What happens is, for well-conditioned, if I have small perturbations in X, then I get small changes in f of X. Remember, I'm making a mapping. This is my mapping. So if I have small changes in X, then this f of X, which is the Y, is also small changes. That's what it means to be well-conditioned. I perturb it, the problem doesn't change very much. It just gets perturbed a little bit too, okay? Ill-conditioned is different. If I make small changes in X, I get large changes in f of X. So a little bit of change in X and Y changes significantly. That's an ill-conditioned problem. And those are the ones we have to watch out for. We want to start setting up algorithms. We want to start evaluating data in such a way that we make sure we're aware of when the problem is ill-conditioned. Because if you have ill-conditioned behavior, you have to make sure that you understand what it's going to do to your results when you're starting to produce decompositions or when you're starting to do any kind of analysis. Ill-conditioned matrices, for instance, are one of the things you have to really be aware of when doing any kind of computations, because they play a big role then in terms of producing reasonable results or complete garbage results computationally. Okay, so we have these two concepts in mind. And what I want to do is then start defining what conditioning means and how we can start getting at well and ill-conditioned metrics. Okay, I'm going to introduce two concepts of conditioning. One is called the absolute condition number. We'll start there, and then we'll do the relative condition number. So let's talk about the absolute condition number. So for me to get at this, what I want to start to do is to define a perturbation. So I have the value of X, and I want to perturb it. In fact, my perturbation is going to be defined as delta X. So I'm going to take my X value and change it by a small amount, delta X. So this is going to define my perturbation. I put the delta here because this is going to be some small quantity. And in fact, we can look in the limit as this is an infinitesimal. And that's exactly what we're going to do, is start to define these things in terms of infinitesimals. So then what I could say is if I change my x a little bit, what I really want to understand is how does it change my output y? Okay, so in other words, how does it change f of x? So what I can look at is in this change, I can define the change in f, which is going to be equal to f of x plus delta x minus f of x. And you start to recognize exactly what we've done in calculus, which is here's a difference. Here's the f with x slightly changed minus f without that delta x, right? So this is the difference. This is this delta f. This is the, what you hope for is if I change this by a little bit, this also changes a little bit. That's in some sense what we're trying to go for being well conditioned. So right away, we're going to start defining concepts here. And the concept we're going to define is the absolute condition number. So the absolute condition number is going to be kappa hat. Okay. Kappa itself will be the relative condition number, which we'll introduce next. But kappa hat is the absolute condition number, which is the following definition. It's the limit as this delta goes to 0 of the supremum of all these delta x's less than or equal to delta, which is the delta f of the delta x. So look what I've done here. Essentially, this is like a derivative calculation, right? If this is the delta f, which is the norm of this, normally when you just do a derivative calculation, you don't take the norm of this. But that's what we're doing here. We're looking at the norm of the change of this f, which is defined here, divided by the norm of the change of x. So it looks a lot like infinitesimals. It's a 0 over 0 if you take delta goes to 0, right? But that's where calculus shines. It makes sense of 0 divided by 0 by defining it in terms of infinitesimals. In practice, we can actually, since we're taking delta goes to 0, we can just simply say, let's just look at the supremum. So the supremum of delta x, delta f, delta x. So this is a ratio of infinitesimals, and all this is saying, how much is f change over how much is delta x change? Where do you get worried? What does it mean to be well conditioned versus ill conditioned from this absolute condition point of view? What you hope for here, just like you do in calculus, is when you do this actually, the limit of this thing is some finite number. What you worry about is when this thing goes to infinity. If it goes to infinity or gets really big, that's ill conditioned. If it stays small or finite or 0, it's well conditioned.
I have a question.
Okay, so because this is a change in f over the change in delta x. And if the delta f is small for the delta x is small, this should go to some finite number. However, if the change in delta x is small and this gets big, in other words, the limit starts to grow, then that's ill conditioned.
Testing.
So that is exactly how we are defining the conditioning itself. Okay? So this is called, this is the definition of the absolute condition number. Now, I've already made the comment, this looks a lot like calculus, and so now we're actually going to use the concept of calculus directly here to describe this condition, absolute condition number, in terms of quantities we've actually used in other fields before of calculus. Okay, so keep this idea in mind, and let me go ahead and erase this. Remember that formula there, or I'll rewrite it probably. Okay. Now what we're going to do, we're going to do the following. Let's assume that f is differentiable. Okay? So in other words, f is some like smooth function and it's differentiable, so I can compute the derivatives. Then what I want to do is actually construct something that you should all be familiar with. Hopefully you've seen it somewhere, which is the Jacobian. What the Jacobian is the following matrix. The Jacobian is a matrix where you take this f and you take the first component, df1 respect to dx1, df1 respect to x2, all the way to dfn dxn, and then df2 dx1. So this is this matrix where every element in this matrix is df of I, df of xj for the ijth entry. Okay? So that's the Jacobian. And Jacobians are often computed when you make a variable transformation. When you make a variable transformation from one coordinate system to another, your dx, your infinitesimal dx's in one coordinate have to be transformed to the infinitesimals, let's call dx bars in the other coordinate. And how do you get that transformation? Is through this Jacobian matrix. So this is a very standard way to compute, in some sense, an infinitesimal, how these derivatives are changing through some kind of coordinate transformation. And remember, that's all f of is. F is just taking you from x to y. And this is the infinitesimal that if you take an infinitesimal transformation, x plus delta x, this is essentially the coordinate transformation you need to get there, or the derivative transformation. In fact, what you really get from this is that df is approximately the Jacobian delta x. So in other words, df over dx is the Jacobian. I just multiply it over. I use approximate here because this is equal as delta x goes to 0. But of course, we're not going to actually take delta x to 0. We're going to take delta x to be some small number, right? So we're going to approximate it with an actual finite small number. Okay, so this is the approximation. So this is what gives you this relationship between changes in f and changes in x. It's through this Jacobian. So with this Jacobian, notice then I have df, and if you remember what I defined the limit as, I defined here earlier that the absolute condition number was equal to the supremum delta x, right? And what it was before, right, was given by here. But delta f now, look at it. It's this j of x delta x, which if I put that over here, what you find is the absolute condition number is the Jacobian. So this is interesting because the Jacobian, when the Jacobian blows up, you know you have problems. What does it mean for the Jacobian to blow up? It means that some of these terms, the derivative is getting very large, going towards infinity. And that's always problematic in a coordinate transformation. And that's what this is telling you. If this thing behaves well, in other words, it's not getting huge, then your absolute condition number tells you that your problem is probably well conditioned. If this gets very big, it's ill conditioned because small changes mean that things change significantly, which means these derivatives are changing significantly. So a small change in x results in this big change in y, and that's exactly where an ill conditioned problem sits. Okay, but there you go. If you take that Jacobian matrix and take its norm, that is the definition of the absolute condition number.
Question?
Yes.
What are the f sub 1 or 2 in this matrix exactly?
Well, in general, these are vector quantities. So this has a bunch of components, that has a bunch of components. Right? So the vector, it's a vector space. X is living in some, whatever, could be m-dimensional space.
I see. So basically you're saying different axis of X would probably have a different function to the errors.
Yeah, so I have to look at every single direction. This is a higher dimensional vector space, right? So I have to compute the gradient along all directions of F. Yeah.
Got it. Okay, makes sense. Thank you.
Yeah, I wish there was a way to, I've been talking about this for years. So since we're all on COVID lockdown, let me tell you a great invention. So if anybody figures out how to do it, I want a pen like this, whatever, you write on the board. I want to be able to hit a button, and when I write, it bolds the letters. So when I write with it pushed down, you would say, oh, he wrote a vector, versus you have to pretend that's a vector, right? And the vector, and you can't tell the difference between my vector and my just straight non-vector quantities. But if you had a pen that could bold things, that'd be amazing.
Maybe just put an arrow on it.
I could, but then that's a lot of arrows. And then even if you did that, you'd still have a matrix, right? And the matrices, you need this to be bolded. And if you put a vector on, then it's, anyway. So I like my invention idea. So if you get that, like, you'll make millions, billions even, because everybody wants to write vectors and matrices on boards. So.
By the way, I think someone else was trying to ask questions.
Yes, someone else have a question?
There was one guy tried to ask questions twice, but you didn't seem to hear it.
Well, he has to unmute, she or he. Anybody else have a question?
Yeah, I was trying to ask a question earlier, but I wouldn't.
Go ahead. Yeah, okay. All right. I'm just going to count on you to unmute yourself if you've got a question.
Can you hear me now?
Yeah.
Okay, cool. So the way I'm interpreting the small change in X and the small change in f of X, does that rule out anything that's non-linear then?
No.
Because
this is generically for any functional mapping that's differentiable, right?
Okay, because like,
in fact, generically, you normally think of this problem as nonlinear, even though we're actually going to reduce it to a linear problem, right? Where the f is just going to be a linear transformation.
Okay, I see. Okay.
Yeah. Okay, so.
Sorry, one more quick one.
Yeah.
So you were talking about the norm of the Jacobian. So do you actually mean matrix norm?
Yep.
Okay.
Yep. So matrix norm is exactly what I mean. Okay. So a more standard way to do this, by the way, the absolute condition number doesn't make as much sense often. It's assuming that most of the numbers are order one quantities, really, at the end of the day, if you want. But relative condition number is what people tend to use more often, because it accounts for the fact that maybe my numbers are all really big, or maybe my numbers are all really small. And what ends up happening if you use the absolute condition number, it can give you very different results depending upon the nature of your data. Whereas the relative condition number normalizes with respect to the data. So let me tell you about relative condition number. Okay, so the relative condition number. How do we define this? Well, it's going to look a lot like absolute, except it's going to have a normalization factor. So essentially, here it is. It's kappa again, but now without the hat, the caret on top. It's going to be the limit, delta goes to 0, of the supremum for all delta x in a ball less than delta. And now what we're looking at is the following. df normalized now by the size of f all over dx normalized by the size of x. So this is an important normalization, because what if all my f's were huge to begin with, right? Just because it would change, this number might be big, but that's just because the data was big. Same thing with this x. So these normalization factors give you a relative score. Relative to what? Relative to the actual values of your mapping x to f of x. Okay? Now we can also simplify this a little bit by just saying, let's just look at the supremum of the dx and df f divided by dx x. So this is our definition that we want to use for the relative condition number. And the relative condition number is actually what's often used in practice. Okay. Again, the interesting thing here is if we assume that f is differentiable, then we can do the same trick before of saying, well, we know what the Jacobian is. And all you're going to do is going to produce a very similar formula to what we had before with the Jacobian, but now with these normalizations that we brought in here, which is the f and the x. In fact, if you do that, here's the only change you get. It's the norm of the Jacobian matrix divided by these normalization factors. So this normalization is now there, and so that gives you now the relative condition number available to you for the data. Now within this relative condition number, I'm going to show you some figures that typically we think about. In particular, concerning how well conditioned is a matrix. When you compute this relative condition number, if this thing is like order 1 to 10 to the 2, this is called well conditioned. When this thing starts to get like 10 to the 6 to 10 to the 16, it's ill conditioned. Okay? And by the way, why do I put 10 to the 16 here? Because it turns out when you're doing computations on any of these devices that we have available to us, you're typically doing double precision operations, right? So you have numerical round off that's around 16 decimal places, 10 to minus 16. So the biggest the condition number is going to get is around 10 to the 16. So basically, if you see 10 to the 16, you're in trouble. Your matrix is so ill conditioned, you should not trust any results that you get from it. Okay? And by the way, I'm going to talk about what it means. What is the physical interpretation of being well-conditioned or ill-conditioned? We're going to get to that towards the end of the lecture, but this is sort of just rough ballpark. So you could take a matrix A, and I'm going to talk about matrices in a minute, and just do the following command, cond A. That computes the condition number of a matrix. And then you ask the question, where does it sit? And by the way, you should be very concerned when you're down here. So when you go solve AX equal to B and the condition number is up here, you probably shouldn't be trusting your values that you get for solutions. In other words, small perturbations will change the answer significantly if you're down here. So it's called an ill-conditioned problem. And it is a big concern when you're doing iterative calculations in numerical and scientific computing, is when you have ill-conditioned matrices, you want to be able to trust your results. But if you have ill-conditioned matrices floating around, you're going to kind of be in trouble if you don't take care of them. All right, so let's talk about then changing this concept around, which is very generic at this point, which is just a mapping from x to f of x, which is y, to now more specific things, which is to think about it in the context of linear algebra. So my mapping now, F, this is going to be, you know, a linear operator, AX. That's what we want to do now. And I want to understand the conditioning related to that, this mapping. Okay? All right. All right, so let's get to it. And let's consider that I have some matrix A. I'll erase this. It's an M by N matrix. And we've been playing around with this with our QR decomposition, with our SVD decomposition. We've always had these M by N matrices floating around. So let's talk about what it means to produce something like a condition number for a matrix. Well, let's go back to our relative metrics, which is the soup, delta x. And on top, what I'm going to have here is A multiply A plus delta x, there's my perturbation, minus AX, divided by my normalization, which is AX, all over delta x divided by x. So that is the definition of, instead of putting, I have now a very specific F to put in there, and so there it is. This is my linear map. This is my linear operator. The matrix multiply is a linear operator. And I want to understand I want to understand how to compute a condition number of that operation. So my model is matrix multiply by A. And I want to understand how well conditioned that is. Well, you can do some, a little bit of toying around with manipulation here. And notice you have A of x here minus A of x there, and then A hitting the delta x. You can do some manipulation here to basically, this is going faster. This lecture is going faster than I thought. I'm going to run out of time. So I'm just going to skip some steps, but you can basically show that this thing here is going to result in the norm of A, norm of x, divided by norm of AX. And that's just manipulating this around. So there's your condition number for this matrix, the relative condition number. So you take the norm of A, the norm of x, divided by the norm of AX. Okay. Now we're going to start relating this to how would I actually, I'm going to start relating this to some things we actually know around the matrices themselves. And we're going to consider square matrices first, and then rectangular matrices second. So let's do the following. If A is square and non-singular. Okay, so that's going to be the first assumption. So I'm going to take this A, and it's now M by M. Okay, so it's a square matrix, and by assuming it's non-singular, it means it has an inverse. Now, the reason I'm going to do this is because what you can show is that, in fact, here is a matrix identity, or easy thing to compute through triangular inequalities, that the inverse of x over AX is less than the inverse A minus 1. And the easiest way to show this is multiply by x. You have A inverse times A times x is equal to x. And then you take the norm of both sides. And then remember that you have certain triangle inequalities. And so this is where you get this. I'm not going to work out the details, but there you go. You have this inequality. So notice that this quantity here shows up right here. So this thing here is less than A negative 1. So what you're going to get then is the condition number is less than the product of the matrix norm and the inverse matrix norm. Okay? So it's kind of interesting. It's starting to set you up to start thinking about computing inverses. And one way to compute an inverse, by the way, is with the SVD. And so we're going to connect this. In fact, that is typically the way to compute an inverse is through the SVD. And so I want to talk about how we would go about then computing this condition number. Okay. So what we're going to do now is talk about what is the norm of a matrix A? What is the norm of a matrix A inverse? And remember, this is for a square matrix. So this is where we can relate this to the SVD. So here's what I'm going to do. I'm going to erase this, move this up, and so we can do some more computations here. And let's for right now just simply define the condition number of the matrix A is equal to A inverse. And there's some constant out front, but who cares? I'm just really looking to see, is this really huge or is it order 1, 10, 100, 5, or is it like 10 to the 14th? That's what I'm really looking at here. So the constant out front is not going to matter so much. One of the things we learned in the SVD lectures is that the norm of a matrix is equal to, that's the 2 norm, by the way, is equal to the largest singular vector, singular value. By the way, how do you get this? Well, you say, well, A is equal to singular value decomposition, right? And so if I take the norm of this thing, notice the norm of this is going to involve a product of the norm of 3 vectors. By the way, what's the norm of a unitary matrix? 1. What's the norm of that unitary matrix? 1. And then it's the diagonals, and that's super easy to compute the norm of that. And it's just going to be the largest diagonal, which is the sigma 1. So we talked about that a little bit in the SVD. So that's what's great. In fact, a lot of times the way you would compute an inverse in practice is you compute the SVD decomposition, and then from the SVD, you compute the inverse. What is the norm then of A minus 1? In other words, the inverse, the 2 norm of it. By the way, if I had the Frobenius norm, I also introduced that concept in the SVD. The Frobenius norm is the sum of the singular values, whereas the 2 norm is just the largest singular value. Well, let's talk about A inverse. If A is this, remember, A inverse is equal to Q sigma V star to -1. But hey, these are all unitary matrices. This is very easy to compute, actually, because the inverse of a unitary matrix is just U star and so forth. So you're going to basically get here B sigma -1 U star. And then if you take the norm of this, what's the norm of a unitary matrix? 1. What's the norm of that unitary matrix? 1. And then on the diagonals, the biggest diagonal now is you took the singular values and you divided them. It's 1 over sigma 1. So the smallest singular value from before, 1 over that is the largest singular value here. So this is equal to 1 over sigma m. Now, as I go to the smallest singular value and I divide by it, that is my biggest singular value for the inverse. So, in other words, with these 2 results, that gives me what I need, which is the condition number. Here it is. It is the ratio of the largest singular value to the smallest singular value. So if you want to compute the condition number of a matrix, this is how you do it in practice. You compute the SVD, you look at this diagonal matrix, you take the first singular value and the last singular value, take their ratio. That's the condition number. Okay? By the way, if A isn't square, then the condition number changes slightly. Instead of it being defined by this inverse, condition number for generic m by n is equal to the norm of A, the pseudo inverse of A. So the pseudo inverse is sort of the inverse. It's sort of like the least square inverse of the matrix A for non-square matrices. And this again turns out to be just sigma 1 over sigma n. Okay, actually, in this case, it's sigma n, right? Let me put that there because it's not square anymore. This is a square matrix, so it's m by m. This is m by n, sigma n. Okay? Okay. So what I've done for you now is just said, hey, take a look. I have ax equal to b that I want to solve. And I want to understand when I solve that, is that a well-conditioned or ill-conditioned problem? What you don't want to start telling people is, hey, look, I solved this ill-conditioned ax equal to b problem, because you really can't trust the answers because small perturbations make a huge difference in the result. That's what this will tell you if you have if it's poorly conditioned or ill-conditioned, okay? So what does it mean for a matrix to be ill-conditioned? Like, what is the physical interpretation of that in ax equal to b? And all of it sits right there in understanding this. So let me draw this for you. And let's start interpreting it. I have a matrix A. And when I do the SVD of a matrix, what do I get? U, right? And I get the sigma matrix and V star. And that's diagonal. These are unitary. Let's talk about this matrix in particular. Actually, it goes to sigma n. So what was our interpretation of these singular values? What we talked about previously when we introduced the SVD is we talked about the fact that these essentially are giving you the principal coordinates of the data of this matrix that you're looking at. Now let's contextualize this in terms of the data I'd given you previously on that mass that I released. Remember, I had 6 measurements. So this was a 6 by how many every time measurements I had. And when you do the SVD, and if I let it go, what would happen? The idea would be that all the data, all the redundancy would get removed. And this thing would collapse down into a matrix, which was not this, but sigma 1, 0, 0. That's the only non-zero element. So let me ask you this. In this case, what it means is those data matrices are not linearly independent. In other words, they're redundant. They're just versions of themselves embedded there. Another way to say that is this matrix is rank deficient. Instead of having, let's say, n columns that are linearly independent, they're not linearly independent. They can be collapsed down to rank R. In fact, in general, if this has something like where it goes to rank R and it's all 0, it means that there's vectors here that are redundant. Another way to say that is when you solve a system like this, if you're rank deficient for your space, it means some of these dependent directions are not linearly dependent. And it means when you try to do an expansion, you try to solve ax equal to b with it, it's ill-conditioned. In other words, there's either an infinite number of solutions or 0. And this is one of the things we talked about. And this is telling you this because when you do the diagonalization, and if you get zeros beyond a certain point, then your condition number for this matrix is going to go to infinity. And what that's telling you is that at least 2 columns of the matrix A are the same. Okay? So instead of this thing spanning some n-dimensional space, it's only spanning an r-dimensional space. And so when you try to write down a solution, it cannot get a solution for you because, in fact, there's an infinite number potentially it could draw from. And so it will give you a condition number that's like 10 to the 16. Okay? Another way to say that is, if a couple of these columns are the same, the determinant is 0. In fact, the determinant is basically looking like it's related to the condition number. So what do we worry about? A system is singular if the determinant is 0. If the determinant is 0, it means the condition number is like 10 to the 16. Okay, so 1 over the condition number is actually like computing the determinant. And if the determinant goes to 0, that means your condition number is going towards infinity. Okay, we're going to talk more about these ideas later, but this is the basic concept behind conditioning. And if you have a condition number that's very big, it means that any small changes are going to change your answer a lot. So little infinitesimal changes make big changes in the answer. And this, of course, is not what you want, especially when some of these little changes are actually just simply due to numerical round off. So if you get a little bit of numerical round off and it changes your answer a ton, how are you going to trust any of your answers? And that's what having a poorly conditioned matrix does to you. If it's well conditioned, you're in great shape. All right, let's end there and take questions.